So the last topic for today is Lagrange method plus Newton's method. So I want to revisit, okay, I guess I'll remind everybody what Lagrange method was. So it was a method for solving constrained optimization problems. And the way we approached it, we had to make this function called a Lagrangian that had the objective function as well as these Lagrange multipliers times the constraints. And then I know that the extreme values of the constrained optimization problem are going to occur at critical points of the Lagrangian. So what I need to be able to do is take the gradient of the Lagrangian, set that equal to 0, and solve that. So that's exactly, well, sometimes, like in the case of the minimum variance portfolio, that was easy because that was just solving a linear system. When the system is nonlinear, it can be more difficult. So the maximum expected return portfolio, this ends up, because the constraints now have this quadratic form in it, it ends up being more difficult. I have to solve a nonlinear function to find the maximum expected return. So I'm going to revisit the example from the slides for Lagrange method. So I was trying to find the minimum or the maximum of 4x2 minus 2x3, subject to these two constraints. And so what I did is I wrote down the Lagrangian. So that's just the objective function. This is the function that I want to find a maximum value of. And then I add lambda 1 times the first constraint and lambda 2 times the second constraint. And now I want to think of this as a function of 5 variables now. So there's 3 that come from the x and 2 that come from the lambda. So it's a function of 5 variables. So when I take the gradient of this function g, I'm going to get a gradient that's a row vector with 5 entries. And I want to find the inputs. So that's x1, x2, x3, lambda 1, and lambda 2, so that this gradient vector is equal to the 0 vector. And so when I tried to solve this in the Lagrange method slides, I ended up coming up with these 5 partial derivatives. I set them equal to 0. And then it wasn't exactly easy to solve, but you could do it. And I think we found that, well, we got lambda 1 for free because of this equation. And then you found that lambda 2 was plus or minus 1. And then that was enough to determine the values for x1, x2, and x3. So in that case, at least it was possible to solve it exactly. And the nice thing about having done that already is we also know that it has 2 critical points. So it turned out the nonlinear equation that I need to solve. So I already know, just from looking at this, the value of lambda 1. So I'm going to not bother solving for that one. So that means I'm solving just f of x comma lambda 2 this time. And so it'll be a function of 4 variables with 4 outputs. And just by looking, so I have to take the partial derivatives of each entry here. So there'll be 4 partial derivatives, and that's what's going to give me my gradient matrix. So this has a partial derivative with respect to x1. This is the only term with an x1 in it, so that's 2 lambda. So I put a 2 lambda here. There's no x2, no x3, so both of these get 0. And then when I take the derivative of this term with respect to lambda 2, I get 2x1. So I just continue that process for each of these 4 functions that are making up my vector-valued function capital F. And that gives me the gradient matrix. And so if I want to use Newton's method for this, I'm going to need some R functions for evaluating these. So here, instead of writing out x as x1, x2, x3, and lambda 2, I've just decided to call all 4 of those things one vector-valued argument x. And so all I'm going to do is make this function f. It's just going to return a vector of length 4 that has the 4 pieces in it from the previous slide. So if you want to compare on your own time, it's basically I've just rewritten this vector-valued function in R. And then I did the same thing for the gradient matrix here. So here I've tried to keep it at least a little bit so it will be human readable. So you can see this is 2 lambda 2, 0, 0, and then 2x1. So that was the first row of the gradient I had on the previous slide. And so if I'm going to enter the values like this, remember R wants to create matrices by putting things into columns. So it fills up the first column first, then the second column, then the third column. So if I want to put things in by row so that I can have it equal to what I'm writing out here, I have to put this optional argument at the end, by row equals true. So this function matrix is going to take this vector of 16 values, turn that into a 4 by 4 matrix by filling in the rows rather than filling in the columns. And so this is going to be a function df, given the 4 inputs, x1, x2, x3, and lambda 2, just creates the gradient matrix. So then I need a starting point. So again, I have no particularly good idea what the starting point should be, so I just chose a vector of 1s. So I need a vector of length 4. So this command just repeats the first argument, the second argument number of times. So this is going to make a vector of length 4 where each element is a 1. Then this time I'm going to do 15 Newton iterations. And again, the Newton iteration, the code for this is actually pretty simple. Once you have the function for the gradient and for evaluating the function, this is all the Newton step is ever going to look like. So I'm just taking x, I'm subtracting my update to x, and I'm storing that again in x. And then if I repeat that, my x is going to follow my sequence of Newton steps, hopefully closer to the value x star that I'm looking for. So code for Newton iterations, very simple. And what I've done here, so these were the solutions that we came up with in the Lagrange method slides. So there was lambda 1, that was fixed, equal to negative 2. And then we found that lambda 2 could be either negative 1 or positive 1. And then the rest of the solutions, just the sign of them was determined by the sign of lambda. So I'd get negative 2, 3, negative 7, and 2, negative 3, 7. So it's the first 3 are just multiplied by negative 1 to get the first 3 of the other solution. And what this big R matrix is showing, so it's showing the values for x1, x2, x3, and lambda 2. So since I got the lambda 1 for free, I didn't bother putting that in here, but I could have. It just would have made things a bit more complicated. What each row is showing is the value after that many iterations. So remember I said my starting point was going to be the vector 1, 1, 1, 1. So after 0 iterations, my x0 is 1, 1, 1, 1. After 1 iteration, I end up at 6.25, 1.25, 11.25, and negative 3.25. And so what we're seeing is each time I do an iteration, it's changing what the values of these things are. And for the first few steps, nothing very extreme happens. And then all of a sudden, in step 3, I went from 1.62 to negative 247. I went from 5 to 81, from about negative 2 to negative 500 and something. But then after that, they get better until finally so this is the reason why I chose, there's nothing magical about me choosing 15 or anything about this problem that suggested me choosing 15. I just happened to get exact convergence to, within the numbers that the computer is capable of displaying after 15 steps. And also I couldn't fit any more lines on the slide. So from a starting point of 1, 1, 1, 1, I ended up getting to within the sort of numerical precision that the computer is capable of doing, the solution that we found theoretically. So the solution corresponding to lambda 2 equal to negative 1. And so this is something we have to be aware of, is there are two solutions. I know there are two solutions. But Newton's methods, if it converges, it's only ever going to converge to one of those. I can't run it a little bit longer and hope that it then tells me what another solution is.
Would different initial values take you to the other solution?
Yeah, well, that might be on the next slide. First, though, I guess I just made some plots. So this is, I couldn't figure out how to put the vector length symbol over here, so I just used absolute value. But what I mean here is xk minus x star. So since I had this theoretical result, I knew what the real answer was. So I just mean the length of the vector, so how far away I am from the point that I'm trying to estimate. And you see at the beginning, with my initial guess of 1, 1, 1, 1, didn't do too bad. And then all of a sudden, it bumps way up to here, but then it takes me pretty quickly back down. And so after about 10, I can't see anything on this scale anymore. So I plotted this on the log scale. So it's exactly the same plot, except now instead of putting the actual scale, I'm just putting the log of the number that was on the y-axis. And so again, you see in the first few steps, nothing very exciting happened. Then it got much worse. And then on the log scale, it sort of has this linear bit. And then it really starts to drop off after that. And so somewhere around here is when this quadratic convergence that I was talking about, that's where that kicks in. And you can see for this step and this step, you can think of the scale here as roughly the number of significant digits. So when I go from this step to this step, I'm getting an increase of it's going to be about one significant digit. Here, I'm going to get an increase of one significant digit. And then after the next step after that, I get an increase of maybe 2 or 3 significant digits. And if I were to keep going, that's just getting better and better. So some observations about this. So from a given starting point, Newton's method converges, if it converges, to a single value x star. So in this case, there are actually 2 values that it could converge to if it were working. And it, just because of this initial condition that I gave it, it converged to one of them. And so starting at the point 1, 1, 1, 1, I got this answer. So here I've just dropped out the value of lambda 1. But I know there's 2 critical points. And so I'm just going to kind of guess that if I start from all 1s and this ends up being a negative 1, maybe if I multiply this starting vector by negative 1, that's just going to flip everything around, and this will be a positive 1. So let's try doing that. So I just put a negative sign here. And so that's going to make my initial vector a vector of minus 1s instead of a vector of 1s. The code for doing the Newton iterations stays exactly the same. And so this is the solution I'm hoping to get. Oh, no, sorry. That's the solution I actually get after this, which is this solution divided by negative 1, which is what I was expecting to get. So yeah, if you try different solutions. But the problem is, in general, we're not going to know the number of critical points. So in this case, I knew that I got one of them, and I knew what the other one was. So that gave me some ideas. So for instance, using negative 1, that might lead me to that other critical point. In general, that's not going to be the case. So usually what you can do is you can get some additional information about the problem. So you can study the problem a bit more. If you read the Lagrange chapter in the textbook, he talks about how to classify a critical point as a minimum or a maximum. So you might know that your solution has, or that the problem you're trying to solve only has 2 critical points. So this is the case in the maximum expected return portfolio. You actually get 2 answers, a maximum expected return and a minimum expected return. And so if you can classify the point that you found as a maximum, then you know that you found what you want. So sometimes that allows you to use this to get an answer to the problem that you want. And if you can't do that, the very best you can do is just try to use multiple starting points. So really what you would do here is use some sort of random number generator to just choose problems. You want to be a little bit smart about it, so you want to choose things that are on the same scale. I guess another thing I should point out here is the starting value that I chose, and that might go a long way to explaining why we get this huge jump here. The starting point that I chose doesn't actually satisfy the constraints of the Lagrange method problem that I'm trying to solve. So I think what sort of happened here is it kind of meandered around until it managed to get into the space of points where the constraints were actually satisfied. And then that's when we got this much nicer looking behavior. It's converging towards the value that I wanted. So unfortunately, if you don't know anything else about your problem, that's about the best you can do, is just try starting points randomly. Hopefully they'll converge to more than one solution. And then you can look at the value at that solution and decide if you've got, at least a local minimum or a local maximum.